This is the limit definition of the derivative based on the idea that the derivative is the average rate of change as the interval becomes smaller and smaller and smaller, eventually closing in towards a single point, never actually reaching it, of course. Now, what we may recall from algebraic limits, specifically limits of rational expressions, is that this will automatically have a discontinuity at x equals a if we attempt to use direct substitution under the assumption that this might be continuous. We would find f of a minus f of a over a minus a, which would result in the indeterminate form 0 over 0. So there's going to be some algebra necessary. We need to find an equivalent form of the average rate of change formula, and that gets to be kind of tricky. Because as we've seen with other rational expressions, that means that somewhere in the numerator we have to produce a factor of x minus a to simplify with the factor of x minus a in the bottom, and therefore remove the discontinuity. Or find the equivalent continuous function. There's a minor problem with that. Or not a problem, but a difficulty. Factoring a complicated numerator to remove a binomial factor can be a little bit tricky. There are times it's not so obvious. However, if we could rewrite this expression so that it can be written with a monomial denominator, life will become much easier for us. So while this is a valid form of the limit definition of the derivative, there's a better one, a much more usable one when it comes to the algebra. So I'm going to suggest this. What we have here really is the average rate of change between our target point a comma f of a and our floating point x comma f of x. That's the formula f of x minus f of a over x minus a. That's the formula that we've developed and are using. Now, I'm going to suggest that this can be written in a much more usable way if we're a little bit creative about how we choose to write the floating point. Right now we're leaving it as x comma f of x because that seems the simplest way to write it for some generic function x or f with some generic input value x that is approaching a. But ultimately, here's what really x approaching a is talking about. The closer x gets to a, the smaller the distance between them. The implication, of course, is that x is some value that is a little bit distance away from the target a. What if we instead choose to write the floating point in terms of its distance from the target? Rather than let it have its own x value, so to speak, that defines it, let's talk about it in terms of its distance from the floating point. What if we let x comma f of x be written as a plus h comma f of a plus h? What if we look at x as being some distance away from a? Swallow that for a moment. So that actually does kind of make sense if you think about what we've done with numerical limits on the very first lesson, what did we do? We had, if x is approaching a, then we used a plus or minus 1, a plus or minus 0.1, a plus or minus 0.01, etc. These are our values of h. They're literally telling us how far away from our target are we. One whole number to each side, 1/10 to each side, 1/100th to each side. Note the format: a plus h, a plus 1, or if you're willing to call the subtraction, a plus -1. So in that case, the average rate of change becomes, instead of f of x minus f of a over x minus a, we get f of a plus h minus f of a over a plus h minus a. Now at first glance, this is going to look awful. It looks like we made it worse. But take a good look at the denominator. The a's cancel out. Now, while the numerator might appear a little uglier than the original form, remember that in order to evaluate the limit, we're going to need to create a factor in the top that matches what's in the denominator so that they can simplify out. It's going to be much easier to produce a single factor of h than it will be to produce the binomial factor of x minus a when we factor the numerator. So a little bit of really not complicated extra algebra up here helps us avoid a much more complicated form of factoring later on. So what we get then is f of a plus h minus f of a over h. How do we write this in the limit? Well, the limit originally had x minus a, or x approaches a. This no longer has an x in it, it has an h. The whole idea, though, is that the value of h is supposed to be getting smaller and smaller and smaller, really approaching 0. So instead of the limit as x approaches a of f of x minus f of a over x minus a, we can use the limit as h approaches 0 of f of a plus h minus f of a over h. This form of the limit definition of the derivative will be considerably easier for us to work through algebraically. Let's look at an example. In fact, let's take s of t is equal to negative 16t squared plus 64. And let's suppose our target value is 2, as we did in the numerical description earlier. Now, we're going to do this two ways so we can see the difference between them. The limit as x approaches 2 of s of x minus s of 2 over x minus 2. Well, we can start by using the formula with x substituted in. minus the formula with 2 substituted in. All over x minus 2. Now, at first glance, of course, the numerator doesn't look all that great, but it's actually not bad. This has no variables. Everything in it can be simplified down until we get a single value. And while nothing can be simplified here, certainly we'll be able to subtract and combine the constant terms later on. So let's start with simplifying negative 16 times 2 squared plus 64. Now, I'm not going to go through all of the tiny little steps of that here. S of 2, as we saw earlier, is simply the height of the object 2 seconds into the fall when it strikes the ground. So, as it turns out, the subtraction of 0 doesn't really do anything for us. Now, our goal is still to evaluate this limit. The problem, of course, is that we cannot do direct substitution. If we put in 2 for x, quite clearly the denominator will turn into 0. Actually, as we saw up here, if we put in 2 for x here, the numerator will turn into 0 as well. So what we would need to do is remove the factor of x minus 2 from the bottom, and in order to do that, we need to factor the numerator until we have a factor of x minus 2. Now, that's not a huge deal. I mean, again, remember, this is a relatively friendly problem, and we're using a relatively friendly value. But that being said, this very much requires your ability to factor things. So here, we can factor out a common factor of negative 16. And then the x squared minus 4 can be factored, since it is a difference of squares. As x plus 2 times x minus 2. And that gets us the factor of x minus 2 in the numerator to cancel with the factor of x minus 2 in the denominator. So what we have then is negative 16 times x plus 2. And this expression is equivalent to the original at all values of x except for 2. But since that's where the limit is approaching, we never actually use it. So if they're equivalent everywhere else, then no matter what other value of x we would put in, what happens with this will match what happened with the original. And as such, we can use this continuous function to get the value of the derivative. Negative 64, as we found by the numerical approach. Now, of course, one of the advantages of the algebraic approach is that it can be easily adapted for other target values. Whereas if we were doing the numerical approach, we would have to go through all of the average rate of change calculations and constructing a table to examine the trend of average rate of change values. This would be easily adapted if we had a different x value. However, again, we have this alternative form of the limit definition of the derivative, which is really what the purpose is here. This was not that big of a deal to factor the numerator, largely because we were dealing with a friendly value of x and a function that really wasn't all that bad. What if this wasn't x approaches 2? Suppose, for a moment, we were working with the same function but suppose this time we wanted to know the velocity at 0.5 seconds. Now we could use, again, the limit as x approaches 0.5 of the average rate of change calculation. But without having to go much further, imagine having to factor something that would produce an x minus 0.5. In fact, really think about it for a moment. How many times have you factored any polynomial and got an x plus or minus a decimal value? In fact, when you really think about it, you've probably never done that, and it might sound a little intimidating. Okay, I'll tell you what, let's come back to that one. Let's come back to that later. Let's go back to here, when our target value was 2. And let's consider what happens if we were to use the alternative form of the limit definition of the derivative. The limit as h approaches 0 of s of 2 plus h minus s of 2 over h. And one of the nice things is all the work is again in the numerator, and it's really not that horrible of a thing to do. It will look so at first, but it's actually not very bad. To do s of 2 plus h means we have to substitute the entire expression 2 plus h into the formula for our function. And of course, for s of 2, it's substituting 2 into our function. Now again, this is a simple enough function that this might not seem advantageous at first. But bear with me. Now again, what we saw on the previous side is that this simplifies down to 0. So all of our work really is going to be in this, where we have to first expand 2 plus h squared. Note that this would be a FOIL, so we would have to do the firsts, the outsides, the insides, and the lasts. And that will give us 4 plus 4h plus h squared. You can work that out on your own. Oh, excuse me, I forgot the negative 16 at the beginning of it. We have negative 16 times 4 plus 4h plus h squared, and then plus 64, minus, remember from the times we've already dealt with that, that comes out to be 0. This part actually cleans up pretty nicely. The negative 16 distributes, and we have negative 64 minus 64h minus 16h squared, and then plus 64 all over h. Note here that the constant terms cancel out. And what we're left with in the numerator is an expression where every term has a factor of h in it. since all we really need is to get rid of the factor of h in the denominator, why not simply factor out a common h from the numerator? Could you factor out more? Yes, but I don't think it's necessary here. Our goal, remember, is simply to break the indeterminate form and produce an equivalent expression. It does not have to be tremendously simplified. Our goal is simply to create an equivalent expression that is continuous for all values of the variable except perhaps the target. In this case, without those h's in the way, there is nothing to prevent us from simply substituting 0 in for h. Oh, excuse me, we don't need the limit anymore for doing the substitution. And we arrive at the same answer. So, what's the advantage of this other method? Well, for one thing, the factoring here is much simpler. That's really the ultimate point here. Now again, remember, this is a very friendly function with a very friendly target value. Remember, even with the friendly function, what if the target value is not so friendly? This is going to be disgusting. On the other hand, this, I bet you, won't be so bad. Because remember, we're going to have to put that into the function and expand it. But it's much easier to expand something with a decimal than it is to factor something with decimals. This would turn into the limit as h approaches 0 of negative 16 times 0.5 plus h squared plus 64 minus negative 16 times 0.5 squared plus 64 over h. And as horrendous as that might look, remember, these are all constants. This whole thing can be evaluated to a single value. This must be expanded as before. We write 0.5 plus h 2 times and FOIL it out. But it's much easier to FOIL this out than it would be to eventually have to factor the numerator and produce x minus 0.5. Down here, what we would see happen is that every term without an h would cancel out. And all we would have to do to factor is simply factor out a common h. That would simplify with the denominator. So perhaps this is a better idea for when functions maybe aren't as friendly, or for when the target value maybe isn't as friendly. So ultimately, what it comes down to is that the limit definition of the derivative that we will be using most often is this. Limit as h approaches 0 of f of a plus h minus f of a all over h. It is an alternative version that will suits our purposes better. It provides us with, perhaps at times, some slightly more complicated work in the numerator, but considerably easier simplifying of the rational expression. Because again, it is easier to factor out a single h from the numerator eventually than it is to have to factor the entire numerator to produce a binomial expression.